in lesson 2 we have seen the basic CFD approach which enables us to solve a partial differential equation as a set of algebraic equations. The basic approach is that we take the flow domain and put lots of grid points, and these grid points are spread throughout the domain, and it is at these grid points we would like to have the velocity of velocity or the corresponding variable which is there in the equation. We substitute finite difference approximations which are valid at that grid point into the governing equations and convert the partial differential equation into an approximate algebraic equation valid at that particular point. And the idea is to solve this algebraic equation in order to get the variable value, for example the velocity at point ij. But what we saw is that the variable value at point ij is expressed in terms of the variable values at the neighboring points, that is at I plus 1j, I minus 1j, ij plus 1 and ij minus 1. So, we have to write down similar approximations at each of the grid points, and then we will end up with a set of n algebraic equations for the n grid points at which we want to get the velocities. So, in the end we would have converted one partial differential equation into n set of n algebraic equations. And the idea is that if we solve all this set of n linearized algebraic equations together, we will be able to get the solution which is the W at these grid nodes. So, we will in this lecture we will see how this particular process goes on. So, we are considering a rectangular duct. We have divided this into 5 equal intervals in the x direction and similarly in the y direction. Although we cannot see it from this picture here, delta x is the same and delta y is the same. So, we have x going in this direction and y going in this direction, and similarly I going in this direction and j going in this direction. We can identify any grid point with two indices I and j representing the ith grid line coordinate line in the x direction and jth coordinate line in the y direction, and the intersection of the ith coordinate line and the jth coordinate line will give us the grid point. For example, if this is I coordinate line and this is j coordinate line, this point here will be ij. And the governing equation, which is dou square w by dou x square plus dou square w by dou y square equal to c, was converted into w at I plus 1 comma j minus 2 w I comma j plus w I minus 1 comma j divided by delta x square plus w I j plus 1 minus 2 w I comma j plus w I j minus 1 by delta y square equal to c. So, at point ij, this is an approximate form of this equation, okay? And we see that if we solve this for wij, if we can solve this equation is for the value of w at I comma j. So, if we know these values, the j plus 1 value, j minus 1 value, then we will be able to get wij. But unfortunately at this stage we do not know what the neighboring points are. So, we take this as the template and write down similar equations for all the points that we do not know. okay, all the points at which we would like to know the velocity, so that we will have a system of equations in which figure all the velocity variables that are unknown, and then we solve them simultaneously. So this is what we are going to look at in today's lecture, with the specific example of this 5 by 5 division of the flow domain. So in this flow domain we have boundary conditions, and since we have 5 by 5 intervals, so you have 6 by 6 okay, 6 by 6 points at which we have the grid points. So there are 36 grid points. These are intersections of the coordinate lines here, and out of this we have the boundary condition that W is equal to 0 on all walls. Okay. So that means that the velocity at this point, which is on the boundary, at this point on the boundary, all those things are known. So it is only these interior points are unknown. So we do not know the value at this point, at this point, this point, this point, at these points marked by a circle. So there are 16 points in the interior at which W is not known. Okay. So we would like to apply this for every grid point at which the value is not known, and then we would like to get a system of equations. So to illustrate this, let us see how we can apply this template here to the first point here. So the first point here is I equal to 1, 2, 3, 4, 5, 6, and j is also equal to 1, 2, 3, 4, 5, 6. So the first point has I equal to 2 and j equal to 2. So we will call this as 2, 2. So if you take the template equation A here and apply this to this point here, so the value of W I plus 1 j comma j, this will become W 3 comma 2 minus 2 W 2 comma 2 plus here W I minus 1 will be 1 comma 2 divided by delta x square plus here this is W 2 comma 3 minus 2 W 2 comma 2 plus W 2 comma 1 divided by delta y square equal to C. Okay. So at this point, where there is no confusion, we can leave out those commas because we have only single digit indices here. So we can leave out the commas and just write this as W32 minus 2W22 plus W12 by delta x square plus W23 minus 2W22 plus W21 divided by delta y square equal to C. And we can see that we have got a specific equation with values here. In order to make further progress, we can substitute all the variables that are known in this. Okay. For example, C is a given value. So, let us take as part of the problem formulation C to be minus 1000. Okay. So, this actually 1 by mu dp by dz. If you take mu to be 0.001 Pascal second in SI units for water, and dp by dz is negative for the flow to be positive in the for the W to be positive. So, we will take dp by dz to be minus 1, and that gives us minus 1 by 0.001. So, that is minus 1000. So, this is in SI units, and we need to have delta x and delta y. So, let us take this in order to get some numerical value. Let us take delta x to be 0.1 meter and delta y to be 0.05 meters. Okay. So, if you know the total length, and if you have divided this into 5 parts, then you can get this. So, this will imply that the total length in the x direction is 0.5 meters and total length in the y direction is 0.25 meters. So, 2.5 centimeters and 0.25, 25 centimeters and 50 centimeters. So, these are numerical values, and these come as part of the problem specification. If you want to find the velocities and all that, you need to know what are the physical dimensions of the domain, and from the physical dimensions and the number of grid points that you want to have, you can fix delta x and delta y. The constant here is part of the equation, and corresponding to the equation you have a certain numerical value. So, you have this, and you also have the boundary condition that W equal to 0 on all walls. Now, if you look at this equation here, wherever there is an index of 1 either for x or for y, that indicates a boundary point, because 1 means that this one here. Okay. So, x equal to 1 is this one. For all these points, x is equal to 1, and all these lie on the boundary. And similarly, y equal to 1, so that is this point, this index here refers to the bottom boundary. Similarly, for anything which is 6, which is the extreme location. So, if x is equal to 6, then that refers to all this boundary, points on this boundary, and y equal to 6 is j equal to 6 is refers to all these points. So, at all these points, if the either the I index or the j index is either 1 or 6, W equal to 0. We can make use of this to simplify this. So, when we specifically looking at this point here, this equation, this is 0, and similarly this is 0, and we can substitute that x equal to delta x equal to 0.1 meters and delta y equal to 0.05 meters, and we can put this as W32 minus 2W22 divided by 0.1 whole square plus W23 minus 2W22 divided by 0.05 whole square equal to minus 1000. Okay. So, this 0.1 whole square is 0.001. So, this is 100. So, this becomes 100 W32 minus 200 W22. This is 400. So, this is plus 400 W23 minus 800 W22 is equal to minus 1000. Okay. So, W22 800 and W22 minus 200 will finally give us 100 W32 minus 1000 W22 plus 400 W23 equal to minus 1000. Okay, so the application of this template at 0.22 has given us this equation. And we can see that this equation has W22, that is the W velocity at 0.22 as one of the variables, and this is given. We cannot solve this equation directly because we do not know what W32 and W23 are. So, we need to write equations for these two things, and when we write those two equations we will find new values. So, let us just write down the equation for this point. In order to get W32 we need to write the equation at 0.32 here, and 0.32 means that I is equal to 3 and j is equal to 2. So, let us come back to equation A and then substitute I equal to 3 and j equal to 2. What do we get? We get W442 minus 2W32 plus W22 divided by delta x square plus, and here it is W33 minus 2W32 plus W31 divided by delta y square equal to C. Okay, so and here again we try to substitute known values of delta x and delta y, C, and this point which is on the boundary, and that becomes 0. And once you substitute that, delta x whole square is 0.0001, so 0.01, so this is 100 W42 minus 200 W32 plus 100 W22 plus 400 W33 minus 800 W32 equal to minus 1000. Okay, again we can add these two to get 100 W42 minus 1000 W32 plus 100 W22 plus 400 W33 equal to minus 1000. Okay, so now if you look at these two equations, we would like to get W22 from this, but in order to do that we need to know what this is, and when we write this equation we have W42, this one, W22 and this. So, we can say from this we can get W22, and we have one more equation. So, we have two equations to get this one, but still W23 is not known and W42 is not known, W33 is not known. So, we need to write those equations also. So, let us just for the sake of illustration, let us try to write an equation for W23, which means that I equal to 2 and j equal to 3. So, if you substitute again in this, and okay, so let us just substitute. So, W33 minus 2W23 plus W 13 by delta x square plus W24 minus 2W23 plus W22 divided by delta y square equal to minus 1%. So, we substitute the delta x square and delta y square, and this is again 0, and we should be able to get 100 W33 minus 1000 W23 plus 400 W24 plus 400 W22 equal to minus 1000. So, this is one more equation, and this is the equation for 2 3, and this introduces 3 3, 2 4 and 2 2, it is already known. So, we can see that every time we write an equation we have new values. So, let us just try to map this out in this to see where we are. So, when we look at point 2 2, so that is this one here, we have the value here, and then 3 2 is this point, okay, and 2 3 is this point here. So, you have these are the, so this is linked to these two. Now, when we write 3 2, that is this point here, we have 4 2, that is this one, and we have 3 2 here, and we have 2 2, and then we have 3 3, so that is this point. So, we are bringing in these points. So, similarly, when we write for 2 3, which is this point here, we have 2 3, and then we should have 2 2, and we have 2 4, which is this point here, and we have 3 3, which is this. So, we have these things. So, we can see that at every point we are involving the immediate neighboring points in our equation, and where the immediate points are on the wall, we know the velocities, so we can substitute them and they do not appear in the equation. But if they are not along the wall, then they are included in the equation. So, this is the template, and for the general point I comma j, we will have the 4 neighboring values which will be coming into this. So, you have a computational molecule which consists of these. So, when we write an equation for I comma j, we can expect to see 4 neighbors plus these 5 grid points linked together by this computational molecule. So, this is the characteristic feature of computational fluid dynamics. This computational molecule depends on the equation that we are trying to solve and the difference approximations that we are trying to make. So, if we make use of another approximation, then the computational molecule may change, and if we have additional terms in this, again the computational molecule will change, and the coefficients for each of these points, again 1, 2, 1, like that, that also depends on the difference formula that we use. So, depending on the type of approximation that we make and depending on the type of equation that we are trying to solve, we will have a computational molecule, and that computational molecule is encapsulated in this template equation which we choose to write. And once we develop this template, then we see that this template will work only for that point, and that point alone is not sufficient. We will have some neighboring points for this type of equations, and we have to put the template at every point, and then we will get a set of equations. So, if we apply this template for all the 16 points, then we will have 16 equations, and all the 16 equations will be such that when you put them together, no new variables are required for us to get a solution. So, we will have a set of 16 equations which together make up sufficient number of equations to solve for all the 16 variables. So, they uniquely determine the solution. Since we are doing a hand calculation and since we need to write 16 equations, it becomes a bit difficulty. So, in the next lecture we are going to simplify it and then we are going to make it into a 4 by 4 matrix. So, we will have fewer number of equations and we will take it down as a tutorial and try to derive all the equations for a 4 by 4 system and see that for this 4 by 4 system we have enough number of equations that when we put all the simultaneous equations we will have a closed system of equations, and it is just a question of solving these algebraic equations. So, that will be the part of the next lecture, in which it is a lecture cum tutorial. We will go through this exercise of for the same equation for the same domain, but fewer number of points. We derive all the algebraic equations and prove to ourselves that these together make up one complete set of equations which can be solved. And then we go through a specific method of solving these algebraic equations which is characteristic of CFD, and then we go through the solution there. So, that will be part of the next lecture.